Okay, so welcome to the lecture of this finite volume method. Now the equation for this Rn in step 1 is needed only to calculate essentially R0. With this formulation there will be no need to compute A phi n. So this is no need to compute in this formulation, as it is some sort of replaced by A at n. So that is why no one, you do not have to or you do not need to calculate this particular term directly as it is replaced. However, some shortcomings are there in this particular approach is the lack of feedback from the, so the lack of feedback from phi n. From the previous iteration value, the feedback is not that into residual. So which may cause the solution to converge to a very different from the exact one due to accumulation of some sort of an round trip error. So this is one of the deficiency of this particular approach, can be obtained with a modified or better version. Now the other class of system is the conjugate gradient method. So that is the other class of system, while the previous one what we have discussed is the steepest descent method, and the present one that we are going to talk about the conjugate gradient method. The steepest gradient method, one property was there that it will always guarantee the convergence, but rate could be low, and that slow convergence is caused due to some sort of an oscillations around that local minima, forcing the method to search for the same direction only. So that because of that algorithm, so to avoid that, some undesirable behavior can be seen, and while doing that search in the direction for different directions for the previous one. So this can be accomplished by selecting a set of search direction like D0, D1, D2 and so on, Dn minus 1, that A becomes orthogonal. So two vectors, that Dn and Dm, are said to be orthogonal to A if they satisfy some conditions like D transpose A Dm is 0. So now in each search direction, the right step size is taken and the solution would be found after n steps, and n plus 1 step can be written as phi n plus 1 equals to phi n plus alpha n dn. Now you subtract this one from this one phi from both the sides, you get the error, and the error at n plus 1 level is, so you subtract the phi from both the sides, it gets En plus alpha n dn. Now you put these things together for the residual vector. So, that will get you minus A E n plus 1, which is nothing but A E n plus alpha n d n. That will let you R n minus alpha n A d n. So, that is what you get, and in this case it shows that the new residual at the n plus 1 iteration level is just a linear combination of the previous residual and this guy A d to the power n. So, now one has to establish another condition, is that this error function E n plus 1, this has to be also A orthogonal. This also needs to be required. Now, this new condition is also some sort of an equivalent condition to find out the minimum point along the search direction of d n. So, now using this A orthogonality condition between E and d n, one can express this condition as d n transpose A E n plus 1 equals to 0, which will be d n transpose A E n plus alpha n d n. Now, which is essentially going to get us alpha n equals to d n transpose R n and d n transpose A d n. So, that is what you get for alpha n. So, this requirement also implies that d n of transpose A error function at n plus 1 is 0, which is nothing but d n transpose R n plus 1 equals to 0. So, if the search directions are known, that means d 0, d 1, d 2, d n, then alpha n can be straightway calculated. Now, the task is to find out search direction. So, once we know the search direction, then alpha n can be calculated. Now, to find out the search direction, one can write this expression for d n plus 1 equals to R n plus 1 plus beta n and d n. Now, A orthogonality, this is a condition, and this requirement of D vector. So, A orthogonality requirement of D vector implies that d n plus 1 transpose A d n must be 0. Now, you substitute this one, now you put this one here and combine these two, one can get the beta n equals to minus R n plus 1 transpose A d n divided by d n transpose A d n. So, that is what you get the beta n. Now, you can express your ADN in using this information. You can express ADN 1 by alpha n and minus R n. So, you get this. Now, you combined all this expression for alpha n, dn, adn and all these things together, you get the expression for beta n, which would be now R n plus 1 transpose R n plus 1 minus R n divided by d n transpose R n, which is writing like R n plus 1 transpose R n plus 1 minus R n plus 1 transpose R n and d n transpose R n, and this guy is essentially 0. So, this boils down to R n plus 1 transpose R n plus 1 divided by d n transpose R n. That is what one get for beta. Now, the denominator which is sitting here in the expression of beta, it can be further extended or it can be further expressed like dn transpose Rn, which is equivalent to Rn plus beta n minus 1 d n minus 1 transpose R n. So, that is R n transpose R n plus beta n minus 1 d n minus 1 transpose R n. This component is or equals to 0. So, this guy becomes R n transpose R n. So, one can rewrite beta n equals to, you can see R n plus 1 transpose R n plus 1 by R n transpose R n. So, that is a nice expression based on the residual vector. One can find out the beta. So, if you find out the beta in that way, then you can put, now if someone has to look at the algorithm for CG conjugate gradient algo, so that would become, now you first choose the residual as starting direction, like d naught equals to r naught equals to b minus a phi naught, and you iterate starting at n unless or until convergence. So, you keep on doing the iteration till you obtain the convergence. So, the next level you choose the factor in D direction, like alpha n equals to dn transpose Rn divided by dn transpose A dn. So, this is the way you choose the factor in D direction. Then you obtain new phi such that phi n plus 1 equals to phi n plus alpha n dn. Now, after obtaining the phi, we need to cross check for the residual. So, you can calculate new residual like R n plus 1 equals to R n minus alpha n A dn. That is how you calculate the new residual using the new value of the variable phi, and then one has to calculate the coefficient to conjugate residual. How? Now, here you get beta n equals to R n plus 1 transpose R n plus 1 divided by R n transpose R n. So, that is how you calculate the coefficient to conjugate residual, and then you finally obtain the new conjugated search direction like D n plus 1 equals to R n plus 1 plus beta n dn. So, this is how you obtain the calculations. So, the one important thing is that also in this particular case, or rather this class of methods, if you use preconditioner, then it can actually improves the convergence rate, improve the convergence rate. So, that is where one can see the utility or applicability of the preconditioner is also very handy in the CG algorithm. Now, if you have a preconditioner, and so you have a P is a preconditioner, and this is also positive symmetric definite matrix, and you multiplied the original equations by P prime, then the problem is that P inverse A is not necessarily, this is not necessarily symmetric. Even if P and A both are symmetric. So, that is the problem. So, to overcome this problem, the Cholesky decomposition is used to write P in the particular form. So, the Cholesky decomposition is used, and that is written like P could be L transpose. That means, and to guarantee the symmetry, to guarantee the symmetry, the system equation can be written as L inverse A L transpose L minus transpose L transpose P equals to L inverse B, where your L inverse A L inverse transpose, this component, particularly this component, is positive symmetric definite. So, this is not only symmetric, it is also positive definite. So, now the CG method can be, so once you use this kind of Cholesky decomposition to get the preconditioner, now this is positive symmetric definite. So, now your CG method can be used to solve for the, now the CG can be used to get L transpose phi, for which the phi can be found. Now, for variable substitutions, L can be eliminated from the equations without disturbing the symmetry of or affecting the validity of the method. So, performing this kind of step and adopting the terminology used with the CG method, the various steps in the preconditioned conjugate gradient method that can be obtained. So, essentially in top of the CG you use some sort of a preconditioner to get a preconditioner or preconditioned CG. Now, what happens to the original algorithm now? Now, previously we have seen the algorithm for the conjugate gradient. Now, what happens to the original algorithm for preconditioned CG algo? So, first is that again you have to choose starting direction. So, that is important. To get that, you calculate R naught B minus A phi naught. Now, you iterate starting at n until convergence. So, that is the criteria. So, the next step you do that, you choose the factor D direction, like alpha n equals to Rn transpose P inverse Rn divided by D transpose A dn. Now, the third step is that you obtain new phi such that phi n plus 1 equals to phi n plus alpha n dn. Fourth step, you calculate the new residual. So, calculate that, like R n plus 1 equals to R n minus alpha n A dn. Then you calculate essentially the coefficient to conjugate residual, like beta n plus 1 equals to R n plus 1 transpose R n plus 1 divided by R n transpose R n. You get P inverse here. So, that is where your preconditioning system would come. So, here you get the P inverse R n plus 1, and here you get P inverse R n, and then you finally obtain new conjugated search direction, like so. This is n plus 1. So, conjugated search direction like d n plus 1 is P inverse R n plus 1 plus beta n plus 1 d n. Now, if you look at from the previous step of conjugate gradient, here you get the new conjugated search directions using beta n and d n, and there is no preconditioner. But when you look at this preconditioning system, these preconditioners are coming to the picture. So, these are actually developed with a wide spectrum of sophistication with varying diagonal matrix whose elements are also diagonal, and for like Jacobi preconditioner and other things. So, essentially these are using the different kind of methods or different kind of preconditioning CG methods, and the different factorizations would lead to different class of problems. So, we will stop here today and discuss the other things in the subsequent class. Thank you.